Hello, good morning or good afternoon everyone, depending on where you are joining us from, and welcome to today's webinar. My name is Chance Millett-Bangs from Business Review Webinars, and I will be your host. It is our pleasure to have EXERGY with us today, who will be discussing how to increase profitability by using engine and industrial waste heat. Today's guest speakers are Anthony Hind, Sales and Marketing Director, and Luca Zodo, Head of Business Development and Domestic Sales. I'd like to welcome you to our webinar platform On24. This webinar is browser-based, so if you disconnect, please click the link you received via email to rejoin the session. All of the icons along the bottom of your screen are the interactive widgets that we have on offer today, so please interact with them all throughout the session. You may ask your questions at any point by using the Q&A widget or by using the questions box, and we will try and get through as many of your questions as we can once the presentation has finished. You may also tweet about the webinar through the Twitter widget, contact EXERGY directly using the Contact Us widget, download additional documents related to the webinar from the resource list, and leave any feedback that you may have on the webinar by completing today's survey. Please use the Help widget if you experience any technical difficulties or require any more assistance. So, without further ado, please allow me to welcome Anthony. Anthony, over to you.
Thank you, Chance, and good afternoon, everybody. We're very pleased to have you here, and I appreciate the introduction and the opportunity to give this webinar. We've got a very interesting turnout already, so without further ado, we will start the presentation. The presentation today is about 60 slides, so we're looking to get this done within about approximately 1 hour time. There's quite a lot of writing on the slides, and we've done that on purpose so that you can take this away and use it as a resource, because I understand it will actually remain online for a year. So feel free to follow on with me today and then refer back at any time. I think, as Chance has already pointed out, you have the opportunity to ask questions, which we'll come to at the end. So please feel free to write down any questions as we go through the webinar, and then we can come back to those at the end. So as already explained by Chance, the purpose of today's webinar is to really cover waste heat recovery from both engines and industrial applications. So the second slide here is an example of what we're going to talk about today. So first of all, we're going to start with a little bit of background on the environment today. We're going to talk about the Organic Rankine Cycle as opposed to the steam Rankine Cycle. We're then going to mention where EXERGY fits into the marketplace. So we're going to give you an introduction to the company, as well as an introduction to the technology which EXERGY has pioneered and now employ on these type of applications. Then we're going to move into some more specifics and some case studies and give you real examples with the economics. So that is the basis. We'll move on now, and as mentioned, if you have any questions or you want us to expand on anything, please feel free to write that in and we will answer you at the end. So the first slide here I'd like to show you on the actual presentation is a graph which explains to you the energy efficiency which has improved the amount of energy produced over the last 20 years. So we have here from 1990 through to 2010, and we have an increase in the amount of power required. Sorry about that, we just had a little bit of a technical hitch, but we're back on the slide now. So the red line here is the amount of extra energy produced because of waste heat recovery and energy efficiency. The blue line is the amount of energy produced by standard means, and together you see the total amount of gigajoules produced of electricity. So it's energy efficiency which has enabled us to get this red bar in the graph, and we expect this to very much increase over the next 20 or 40 years, as you see in the next slide. So here we are on global electricity by source, and you can see that the renewables is expected to grow and actually be one of the most, or to be the largest supply of electricity by the year 2040, with a variety of different solutions such as hydro, wind, solar, and other renewables. And the other methods of electricity generation will still grow, but not to the same degree. Moving on again, one of the things that greatly affects whether heat recovery is installed is the government policy. This graph actually, this world map here was done in 2012 and 2013. And actually, if anything, the world's moved, unfortunately, a little bit backwards since that period. However, with the renewed discussions between the world leaders towards the end of this year, in December, I really hope, and I think people are demanding, that governments take more action towards implementing energy efficiency law. So let's see what happens, but we're certainly optimistic that not only do these solutions make economic sense, but I'm hoping that governments will support that. The International Energy Agency has underlined 3 main measures that can be the drive in the direction to get increased energy efficiency. The first one they mentioned, which I think is obviously very important here, is improving the energy efficiency within industry. Secondary to that, it's targeting specific coal-fired power stations. And thirdly, it's looking at renewable-based power. Obviously, the talk about today is going to concentrate on the first one, and that is improving energy efficiency in industry and in power stations. And honestly, if we talk about low-hanging fruit, this has got to be the way we look. Making a new power station, making a new industrial development is, of course, expensive. And it's something which captures headlines. Building wind turbines captures headlines. Solar panels captures headlines. However, there is a huge amount of low-hanging fruit by simply increasing the efficiency of existing installations. So here we're looking specifically at the most energy-consuming industries. And we highlight a few here: the oil and gas, iron and steel, refineries, petrochemicals, and cement. I'm pleased to say already we have certainly people from the first 3 areas here on the call today. So we can specifically speak about the applications we've got later on referring to these 3 sectors. But also, as mentioned, we're going to talk about engine heat recovery as well. I'm going to hand over to Luca for the next 2 graphs, and then we'll switch back again. So thank you for the introduction.
Yeah, thank you, Anthony. Welcome, everybody. So the next graph shows one case, which is the steel making industry. And this case is quite important because you can see in this graph how different and how much we can do around the world for energy efficiency. So let me explain this graph. On the horizontal axis, you can see, let's say, a specific thing of this industry, which is how much of the steel is produced by electricity, so with electric arc furnaces, while in the vertical axis, which is the one we are most interested in, is what is the specific consumption for the production. So for each ton of steel, how many tons of equivalent oil we need. So you can see that we can go from a very efficient production lines, as you can see, let's say Europe, UK, Germany, Italy, Turkey, Egypt, Spain, to very inefficient ones like India, Russia, and especially South Africa. So the difference between South Africa, which is the worst in this graph, and let's say Egypt, which is the best one, obviously gives an idea of how much we can do in terms of energy efficiency in the steel industry. So here you see from 0.75 tons of oil equivalent per ton of steel to 0.15, which is really a big difference. More or less the same we can see in the next graph, which is relevant to another industry, the cement industry. So in the case of cement, again, here you can see ratio going from 0.06, which is, let's say, India, the best one, tons of oil equivalent per ton of cement, to 0.11 of Sweden and Portugal, which may be affected by, let's say, very old plants, but for sure very inefficient. So the idea is that in steel, in cement, and in all the other applications we will talk about today, there is really much to do.
Well, thank you, Luca. I think those numbers are quite surprising. So we're going to pose a couple of questions now, but we're going to answer these ourselves, so there's no need for you to try and answer. So what we're going to go through is, what do we mean with the efficiency improvement through heat recovery? And we're also going to talk about which technologies are the best to use, and which resources can be exploited in the most efficient ways. So, looking to answer those three questions, we're going to cover now the organic Rankine cycle generally. So ORC is the ideal solution to recover waste heat from industrial processes and engines, which give us a low to medium enthalpy source. So we're going to cover specifically when to use ORC and what ORC is. So starting with a very simple explanation of the organic Rankine cycle process. On the right-hand side of this page, you see a simplified ORC diagram, and on the left you see an explanation. So if we look at that diagram, and I'll just talk you through it. On the left-hand side of the diagram, you have this red and yellow heat flow. This is basically the waste heat recovery system from either the engine or the industrial process. So if you can imagine that the heat exchanger here is installed in the exhaust of the cement plant, in the exhaust of the steel plant, in the exhaust of the engine. And it is used to heat an intermediate fluid. That could either be oil, it could be water becoming steam, or it could simply be hot water. Equally, in a refinery process, this could actually be the stream itself. So there would be no need to have an intermediate fluid if this heat is being recovered from a fluid in the first instance. So that intermediate or direct fluid passes through a heat exchanger, which is where it interacts with the organic Rankine cycle system. So the beauty of having this separate heat exchanger means that the process is not affected by the organic Rankine cycle. We are separating the two systems, with the only contact being this heat exchanger, which is always provided by the organic Rankine cycle supplier and is a key part of our equipment. This heat exchanger allows the organic fluid to vaporize, making the organic fluid into a gas. That gas is taken to the organic Rankine cycle turbine, which in this case is an EXERGY-specific turbine. It expands within the turbine, driving the generator, and this is what gives us the energy. After that, it leaves the turbine, still as a vapor, where it passes an item which is unique in the ORC cycle, which is called a recuperator. This helps recover a little bit more energy from the heat of that fluid, and is used to later preheat it. Then it passes through a condenser, which turns the vapor back into a liquid. That condenser can be either liquid-cooled or air-cooled, depending on the environment. Finally, a pump, which just gives pressure to the cycle. And then we have this liquid circulating again. Okay, let's have another question at this point, which we can introduce together. When to use the organic Rankine cycle technology instead of steam technology? So this is a very, very common question we get. And it's very important. We're not ever trying to sell a technology which is unsuitable for the correct application. It is not in our interest as a technology provider to try and trick a market. What we're aiming for here is profitability of heat recovery. So we want to always recommend the correct solution. So in specific applications, organic fluids are the only choice, or are the more efficient choice, or the more cost-effective choice. Some applications, steam is the better choice. So we produce over the next page a very, very simple chart. This is not the law, this is not a rule, this is just a general basis for the discussion. So at small sizes and at relatively low temperatures, ORC is a very, very good choice. You reach a point when you could have either steam or organic Rankine cycle. And you reach a point when only steam is the best solution. Now, you could use ORC in any application. So at very high temperatures and very large sizes, you could still use ORC. So why don't you? The reason is it becomes less cost-effective than steam. However, if there's a specific restriction in the environment, such as a lack of availability of water, it may be a conscious decision to use ORC even when it is not the most cost-effective or the most efficient solution. However, generally, it is better to use steam when you get to high temperatures of exhaust. So let's talk about a lot of gas turbines, for instance. If I'm talking about a 50 megawatt gas turbine, it's very likely that steam will be the more efficient and the more cost-effective way to generate electricity. However, if we're talking about a group of engines with an exhaust temperature of maybe 300 to 400 degrees centigrade, it's very likely that ORC is the more efficient, economical, and simple way of doing that. Same goes for the industry. It depends very much on the temperature, it depends on the complexity, and it depends on the size. So over the next page, we've given a little bit of a summary of each. And you can see here that we're definitely an ORC supplier because we've given a rather more positive response to the ORC. But nonetheless, I'll run through each one and we'll sort of describe it for you. So first of all, for your information, ORC technology, even though there is more in the cycle than necessary with a steam turbine, the items themselves are generally smaller, simpler, and more modular. Flexibility of operation. ORC is extremely good at working down to very low loads, and I'm talking approximately 10% of the input power of the nominal. So ORC is extremely flexible, and if you have a process or an application where the engines may vary in load, then ORC can be a very good solution. Water consumption. By using an organic fluid, which is a closed loop, and by having an air cooler, it's possible to have a plant with no steam, no water consumption whatsoever. The fluid consumption of these plants is very, very small and is simply brought in as a spare fluid, usually in a container every year, every 2 years, something like that. So again, for chemicals, for fluids refilling, there's very, very little to talk about with ORC. It really is a standalone, low-maintenance type of unit, more like an air conditioner than a typical Rankine cycle system. Also, something we do see as an advantage, as an ORC supplier, we basically supply all of the equipment. Whereas it tends to be with steam, you buy a steam turbine from one guy, you buy the piping from another guy, and you need an EPC to put it together. It's not always the case with ORC, but that could also be a reflection of the smaller size of the plants. Associated costs. ORCs do not need the same scale of foundations. We have typically seen approximately 1/3 of the overall weight of foundations for an ORC system than for a steam turbine plant. And this is just because the ORC turbine is very simple, relatively light, and as such, the foundation requirement is generally less. All of our plants are set up for remote operation, which actually means we operate them and can monitor them from the factory here in Italy. So it's very, very typical that people want to reduce the maintenance and reduce the operational cost of their plant. They look towards ORC and they look towards remote unattended operation. And also, of course, not having to have a qualified steam operator on the site is a key advantage as well. Sorry, Luca is going to bring something in?
Yeah, this, for example, this is very important for productions which are typically not continuous. For example, in steel production, you have usually 1 day off per week, and you want a system which is able to automatically stop and restart when the oven is off.
Okay, so moving on from that, we then have maintenance, which I think I've already covered, and cost of the system. So at the right size, ORC is okay and can be significantly cheaper than a good quality steam turbine system. And when I talk about those sort of sizes, really we're saying, it's very difficult to put specific sizes because it really depends on the temperatures we're talking about. But I'd say for a industrial process, so a cement plant or a steam plant, up to about 8 megawatts is where ORC tends to give you a better overall cost efficiency solution. Both of them are proven technologies, and then additional power produced. So here we're saying steam is potentially more efficient, but bear in mind that steam is generally used at higher temperatures. So at lower temperatures, steam may not even be an option, let alone more efficient. And then at the border point, you get the point where both of them are as efficient as each other, and at high temperatures, steam can be more efficient and usually is more efficient at the very high temperatures than ORC. So moving on to exactly what EXERGY do. So EXERGY is originally a power plant design company. So we have about 15 years experience as owner's engineer, as an engineering company helping people realize power plant solutions. We are active now in geothermal, waste heat recovery, biomass, and solar. Solar being CSP, concentrated solar power, where we use the ORC to recover heat from hot oil in a solar plant. We have experience with all of these, and at the moment it's geothermal which is, for us, leading the way, but waste heat recovery, certainly a number of plants, is a very, very close second, and it's something we are committed to seeing growing in the coming years. EXERGY really is involved in the entire cycle, and that means we design everything. We designed and patented our own type of turbine. We patented it in-house. We do the full engineering of the cycle, both hot end and cold end, in-house. We obviously then do the project management, and then we look after the equipment, and as mentioned, we can monitor the operation online. We make units as small as 100 kilowatts, but honestly now we're trying to escape that market a little bit, and we're concentrating on the bigger plants. So we got 10 megawatts on a single turbine so far, and nothing's to say we're not going to get bigger than that. And the sort of projects we're looking at the moment are generally ranging from about 1 megawatt, which we have experience of selling as recently as a couple of weeks ago to a refinery, up to about 25 megawatts, which is using, in this case, 2 turbines in a geothermal plant. So on from this, we're going to give you a little bit of understanding as who EXERGY is. So my accent may not give it away, but we are an Italian company. We're based close to Milan, very close to Malpensa Airport, and we have our factory and offices here. But we're part of a much larger Italian holding, which is called SECI Holding, and is part of the Macaferri Industrial Group, which is a privately owned, very diverse, large Italian industrial group. This chart gives you a little bit of information as to the activities of Macaferri and SECI. It's as diverse as environmental engineering, right up into even making cigars from Cigaro Toscano, as you see there. In there we have a big energy group. So we have a biomass company, we have a solar company, a biogas company. You see EXERGY below that. Then we have some wind turbine holdings and a combined cycle holding company as well. So it's a very diverse group. And this gives EXERGY the sound financial backing that a company needs to develop a product, bring a product to market, and stand by that product. And we're actually very lucky. We have the flexibility of a small company. We have the financial strength of a very large company. And being privately owned, we have the ability to really pursue a market based on a long-term strategy rather than based on quarterly or yearly results. And as someone who's previously worked for publicly held companies, companies on the stock market, I do see a great advantage working for EXERGY and being able to pursue this really long-term strategy. A little bit more on this. It shows our worldwide presence as McAfee, and it shows the number of employees and the revenues we have. So we have revenues of over $1 billion a year and more than 5,000 employees. And really, EXERGY is one of the big contributors at the moment. We have got a turnover of about $100 million this year. So what is the brainchild of EXERGY, and what is our key product is the Organic Rankine Cycle, and the heart of that is our Radial Outflow Turbine. So this idea, this concept, the prototype was all part of our CEO's strategy. We were already working inside the ORC cycle, design and supply, and we decided to develop and patent our own turbine. And this turbine has really been an absolute success. We are very, very lucky and grateful to have this in-house. And we're going to explain this turbine to you a little bit more. However, we are able to have an overall cycle design which gives us a higher efficiency than our competitors due to this innovative idea regarding the turbine. And this is the Radial Outflow Turbine. So if we move on to how the Radial Outflow Turbine works, you've got the red arrow here, which shows the axial entry of the fluid into the turbine. We then have yellow arrows, which show the fluid expanding across a stage. And on this particular turbine we have drawn here, this representation of a turbine, you see 3 radial stages. So that means the fluid moves radially outwards, passing through 3 moving radial stages. We can have up to 7 stages on a single disc, but in this case, for the simplification of the drawing, you see just the 3 stages. So I'm going to talk a little bit about this turbine and tell you some of the key advantages. So first of all, we're going to start with a very basic advantage of the radial outflow turbine. The idea of an expansion turbine is that the fluid moves from a smaller area to a bigger area. It expands within the turbine. A very simple concept then is if that fluid moves out across a disc, it has a larger volume as it moves out across that disc all the time. So this natural expansion as it moves across the disc gives us a very, very good expansion ratio compared to an axial turbine or a radial inflow turbine, which our competitors would use. It's also the same as a steam turbine. A steam turbine is usually an axial turbine. So again, we have this very good expansion ratio on this type of design. We also have, which I'll get to the reasons in a minute, low vibrations. We have a very good pressure differential across the disc as this fluid moves outwards. And we have a very simple construction. Because the tip speed is the same, the blades actually are straight, which you'll see again on another slide. So the radial outflow turbine allows us to reach a higher efficiency and flexibility when compared with the axial and the radial inflow turbines. So this next graph is a comparison and a little helps me with the explanation of a radial outflow turbine and an axial turbine. On the left here you see the radial outflow turbine, and on the right you see the axial turbine. So I'd like to point out just a few things from this graph here, from this diagram. If we look first of all at the radial outflow turbine, this gives you a clear explanation of how it works. You've got the fluid coming in centrally axially, it's then turned radially, it then expands out through the stages on a single disc. You'll notice that we've marked the center of gravity in the distance from the bearings. So in organic Rankine cycle systems, the unit is always overhung, which means the bearings are on one side of the disc. So we have managed to minimize the distance B. So this is the distance of the center of gravity of the disc to the bearings. By minimizing that distance, we minimize vibrations. If we look at an axial turbine on the right, you'll see a number of things here. First of all, we have two discs as opposed to one disc. Why is that? It's because each stage is on a separate disc. So in this case, we have a two-stage axial turbine as reflected by the two discs on the shaft. You'll notice the distance B, i.e. the distance from the center of gravity to the bearings, is significantly larger. If you go to a two-stage axial turbine, you have potentially higher vibrations. If you go to a three-stage, you have to move that center of gravity yet further from the bearings, which means you have again higher vibrations. And generally speaking, three-stage is the maximum you'll have on an axial overhung unit before the vibrations become too significant. Also good to notice here that the blade height of the axial turbine increases as it goes from the inlet to the outlet. So that's as the fluid moves from the inlet to the outlet. That blade height is the only way that the fluid gets to expand. You have to have a small blade at the beginning and a large blade at the end. And you're very limited on what is practically possible in terms of blade height. Small blades create a lot of turbulence at the tip and at the inside. Large blades, you end up with very high speeds at the tip and also weakness within the blade. So the only expansion ratio advantage you have with the axial turbine is with blade height. Whereas with the radial outflow turbine, as previously explained, you have both blade height and expansion across the disc. So you have this very good expansion ratio. So really the reasons we have this excellent efficiency are larger number of stages, better expansion ratio, and, as I've already mentioned, the lower vibrations. I said up to 6 or 7 stages on a single disc allows us to exploit higher enthalpy drops. So this is particularly important on heat recovery applications that we're discussing today. Basically, if you do a heat recovery application, you have a large enthalpy drop, and you want to design each stage of the turbine to suit the enthalpy point where it is operating. If you can do 6 or 7 stages compared with a maximum of 2 or 3 stages, you have that opportunity to design each stage for each specific enthalpy zone. And we end up with significantly higher efficiencies. And what we actually see on the turbine, and to give you a real number here, is potentially between 7 and 9% higher efficiencies on a turbine. So we're talking about an operational efficiency and an isentropic efficiency of the turbine of around 90%. And that really is unique in the marketplace for a low-speed direct drive turbine. So what we've got here is just a couple of videos, which will give me a moment to drink some water, but also give you a chance just to see how an axial turbine works and then how a radial outflow turbine works. Or not. No, unfortunately the videos aren't working today. That is obviously disappointing. I hope what we'll do is maybe we can ask Chance to email direct YouTube links to these videos after the presentation today. I'm sorry to say they are not playing. But basically it was just 2 short videos, animations, explaining the route of fluid through an axial turbine and then the route of the fluid through the radial outflow turbine. So we'll definitely find a way, maybe by the end of the webinar today, to show you that radial outflow turbine. So this is a study done to show the difference in efficiencies between radial and axial efficiency. And this was actually a study done by the Politecnico of Milan, and this was done as an academic study. So this is theoretically, when we were being very conservative, we found that each stage of the unit could be a few percent higher efficiency, up to about 4% higher efficiency. But as I said, we can also give more stages. So if we have each stage operating at a higher level of efficiency, but then we give more stages, we can overall have a significantly more efficient turbine. As I said, up to about 7 to 9% more efficient than an axial turbine. So we're on to a slide now which answers one of the questions we've already received, which is the differences between radial outflow turbine, radial inflow turbine, and axial turbine. So up until now, I've really tried to describe to you what the differences are physically, and I've said why the radial outflow turbine can achieve a higher efficiency. So now let's just try and summarize some of the advantages. So we've got a number of different items here, and I'll try and bring the relevance of each one up. The first thing is number of stages. A radial inflow turbine, for your information, is a single stage, high-speed turbine where the fluid moves from the outside to the inside. This is basically looks a little bit like a turbocharger running in reverse, to give you an example. So it is a single stage, and it relies on its high speed to give you a good efficiency. And it does have a higher efficiency, but it tends to have a higher efficiency at very discrete conditions. So it works at a very set condition at a high efficiency. An axial turbine is the one we've already described. That can have up to 3 stages, and the radial outflow turbine can have up to 6 stages. So that higher number of stages tends to give us a higher efficiency and a variety of operating conditions. Off-design performance. So radial inflow would generally have a poor off-design performance unless it has inlet guide vanes, which we've labeled here as IGV. Axial, again, does not have great off-design performance in comparison to the radial outflow, where the large number of stages gives us this advantage of a higher performance at lower loads and changing conditions. Rotational speed. Now, this I would see as a key advantage to both axial and radial outflow turbines. What we're aiming for here is a simple heat recovery system which gives you reliable, unmanned, low-maintenance operation. A radial inflow turbine is a high-speed turbine which relies on its speed for efficiency. If you're giving a gearbox, which they require, you are gaining an efficiency downside because the gearbox has losses, and also a maintenance downside because a gearbox is another potential failure point, as well as a unit which does require maintenance. The direct drive of both the axial and the radial outflow turbine gives a real advantage. Vibrations and noise. Again, I've already mentioned to you that the low vibrations of our turbine gives a significantly longer bearing life and really helps the maintenance of the unit. The high-speed turbine obviously is affected by some noise and also by wear on the bearings because of the high speed, and the axial will have higher vibrations. Design complication. Our turbine, maybe towards the end we can show you a few more slides on the actual design of the turbine. However, the actual unit is this single disc with rings of blades attached to that single disc. It is made from a very, very low number of pieces, and it is straight blades, which means the blades are not made separately. The blades are made as each stage is a single piece of material, and it is milled as a single piece of material. So we have a very, very simple, straight-bladed design, which means construction is very robust, very reliable, very simple. And again, this varies from radial inflow, where you have a very high-speed turbine, you have each blade doing an awful lot of work, a lot of energy per blade, and then with an axial turbine you have twisted blades, which are quite complicated to make, quite complicated to replace. O&M. we've managed to provide a very simple O&M strategy where the only parts of the turbine which need maintenance can be removed in a single unit. We call that the mechanical group. It contains the bearings, it contains the oil lubrication system, and it contains the seals. And those can be removed and replaced in a single block in approximately 6 hours. And that is without losing any organic fluid. So the only maintenance on the turbine is a very, very simple procedure. And that really is unique in the market and has given us a great advantage in the plants which we have already installed. The next thing is the pressure of the cycle. And here both the axial and the radial outflow turbines have the advantage of a low pressure cycle. A low pressure cycle means less expensive valves, simpler piping, and simpler maintenance moving forward. Again, now we talk on to different cycle types. And again, this saturated cycle is a low pressure, simple cycle, which generally is easier to operate. Working fluids. So there's the option for flammable and non-flammable fluids. We're very lucky that the radial outflow turbine gives us the opportunity to really select the fluid for the application. So typically we can use a hydrocarbon, which is a flammable fluid, which is the least expensive solution, or we can use a refrigerant, which is a more expensive solution but non-flammable as required. Moving on, we have the turbine cost, which our simple design allows us to produce turbines at a relatively efficient price. And finally, turbine isentropic efficiency. So I think here we've got 85%. Actually, we're now measuring, as I said, 90%. So since then, we've gone up to really a very, very high efficiency on the turbine, which is better than axial and very similar to radial inflow. But because we then eliminate the need for a gearbox, overall our cycle efficiency is the highest on the market. So I've really hoped to cover there a little bit of an introduction to the radial outflow turbine and to the organic Rankine cycle process. And I really thank you all for your patience at bearing with us through that part. The reality is, what goes into the cycle is less important to you than what comes out. The takeaways from what I've explained, I hope, will be the fact that we are an experienced, reliable company, the fact that we have an interesting technology and innovative technology that we have designed and patented and installed ourselves, and it has been successful. So what is important, and what we're going to devote the second part of this webinar to, is how that enables you to do economic heat recovery projects. So we're going to go through some key examples, give you some figures, and let you see what makes a profitable project. But before we get to that, I'm just going to ask a couple of questions. And here you get to interact. So if you're still awake this afternoon, grab yourself a coffee and click on their answers. So we're interested to know, as who is attending this, are you more interested in heat recovery from industry or heat recovery from engines or gas turbines? So are you from the power generation sector or are you from the industrial heat recovery sector? And I'll give you just a minute now to click on one of these. Okay, so here are the results from that. So we've got 40% interested in industrial heat recovery and 61% interested in engine and gas turbine heat recovery. Now looking at those numbers with a 0.1, that means we must have 1,000 people on, I guess, which is an impressive situation. So thank you all for voting on that. So that will help us discuss the points a little bit more in the coming moments. I'm now going to hand over to Lucas Zodo, my colleague, who's going to speak about 3 specific examples for you.
Yes, thank you, Anthony. So we're now going to speak about the applications that we have evaluated in terms of technical features and economics for 3 examples of industrial and power generation heat recovery. The application of the ORC in heat recovery, as Anthony has already anticipated, can be on many different industries. So we can say cement, steel mills, glass mills, furnaces, and also on power generation like gas turbines or engines and compressor station. So we will start with a steel mill case. This is the case of a quite, let's say, small steel mill. So we are talking about approximately 60 tons of steel per cycle, and what results from the heat recovery is a 2 megawatt net electrical power. So in the picture you can see our installation. This is a 1 megawatt installation on a steel mill in Italy, and on the flue gas line of the electric arc furnace. So on a steel mill you can do 2 kinds of heat recovery usually, and this is the most, let's say, what we call the hot one, and then there is the cold one. Let me explain you what are the differences. So in the hot one, you put a heat exchanger inside the flue gas line. So you intercept the flue gas line, and before cooling the flue gas down, you pass through a heat exchanger. You produce pressurized water, which goes to the ORC at about 200 degrees. And this is the first kind, and this is what we're talking about in this case study. The second way is to use the existing cooling system for the flue gas line, because in every electric arc furnace you have a cooling system for the flue gas line, and usually operates at about 90 degrees, 100 degrees, usually not more than 120 degrees. Obviously, what happens is that the efficiency of the heat recovery system will be lower, but as an opposite effect, the cost of the system implementation is much lower, because there is a very, very small intervention on the flue gas line. So getting back to this case, we have flue gas which are quite hot. They come from a first cooling, in this case, to about 450 degrees, and they're cooled down in the heat exchangers to about 250 degrees. The investment needed for this kind of a plant is in the range of 5.5 million euro. Sorry for the mistake, it's not per year, it's €1 million total. And the operational cost, these are euros per year, and it's in the range of 100,000. We have taken as an example 7,200 hours of operation of the plant, which is a typical number for a steel mill. So the result of this analysis we are showing in this table is divided between different scenarios of electricity cost. So we take, let's say, a normal cost of $70 per megawatt hour, which is a typical industrial cost in Europe, and then we have taken other figures which can be compared to this one with some incentive program. For example, here in Italy we are more at about $150 per megawatt hour, or in areas in which there is a shortage of electricity, so you can go up to $200 per megawatt hour. So having in mind the capex, the investment needed, we can say that the net cash flow per year will vary from about 800,000 euros to about 2 million euros per year. Obviously, the payback time and the economic figures, so the internal rate of return of this project, will vary accordingly. So we go from, in the case of $70, we go to about 7 years of payback, which is not very attractive for a typical industrial investor. We go to $150 at about 4 years, which may be more near your expectation in terms of return. So steel mills are a particular case. As I mentioned before, in a steel mill, the heat recovery part is quite critical. So sometimes you may be more interested in a less impacting heat recovery system using the already existing cooled duct. The second case is the heat recovery from internal combustion engines. So in this case, we are talking about the 7 engines, Rolls-Royce, producing about 9.6 megawatt. And from these engines, we can recover a total of about 5 megawatt net. So in this case, we are not talking about saving energy for the industrial production, but we're talking about increasing the efficiency of the system. So in all the cases in which there is a power production made in open cycle, so with an internal combustion engine or with a gas turbine without a heat recovery system, in all these cases, the application of an ORC module can really increase the efficiency and thus reduce the cost of production of electricity. So in this case, the investment is in the range of 10 million euro. The operational costs are still very low because compared to the internal combustion engines or the gas turbines, the operational cost of a ORC turbine is really, really low. Operating hours are higher, so we have taken almost 8,000 hours per year at full load. And the gas temperature, the flue gas temperature, is a bit lower than in other applications because obviously the efficiency of the engines makes it 380 degrees at the entrance of the ORC. Also, the return temperature of the gas to the stack is in the range of 140 degrees, which is much lower than the 250 that we have seen before. If we look at the system, we can see that the flow diagram shows, in this case, the engine groups going to a stack, and before, let's say, the chimney, we have the heat exchanger, and then the system is exactly as Anthony has described before. In this particular case, we would like to use an air-cooled system. The air-cooled system makes the ORC even more automatic, let's say more independent from all the rest of the plant. And it's really a standalone module working beside the power production unit. So in this case, for example, we have 4 bays, 8 fans of air-cooled condenser. We have an ORC, you can see in this layout, composed of expander, generator, hot heat exchangers, so preheater, evaporator, and superheater, and recuperator. As you can see, this is as small as 30 meters times 30 meters. So it's really a very simple and compact system to produce 5 megawatt more for this plant. Here you can see a side view of the system. Again, this is quite a small unit. Again, if we look at the electricity production figures, again you can see that you can vary from quite long return of about 7 years to a very short return of about 2 years, depending on the cost of electricity, which obviously make more or less profitable the investment. Obviously, this case is particularly interesting, for example, for electricity production on islands or in isolated grids, where usually the cost for bringing the fuel and the cost for operation are much higher than in normal power plants, in, for example, Midland. Last case study is a glass mill. In the case of the glass mill, again, we have a similar unit in terms of dimension, so it's a 4.6 megawatt net. Here, the flue gas are at the intermediate temperature, so 420 degrees in, 200 degrees out. We have a 10.5 million euro investment and 8,000 operating hours. This is, let's say, a rendering of the system with the 6 fans, air-cooled condenser. Again, it's very similar to the one you've seen before, and this is exactly the plant we have just installed and started up and successfully commissioned in Bulgaria on a glass mill. And this is, unfortunately, I couldn't put a picture here, but this is exactly how you would see it if you visit the plant. So the business plan, you can see that, again, we are talking about a payback time which goes from 6 to less than 3 years at the values that we have discussed before.
Okay, great. Thank you, Luca, for those specific case studies. We've received some questions as we've been going through that, so we'll come to those in just a moment. But before we do, we just wanted to summarize with a few of the references. So the next slide here, we just show you the breakdown of how many plants we've done for each type. So we've done 18 geothermal, 17 heat recovery, 1 CSP, 5 biomass. And please, bear in mind that we are a relatively new company to the market. So we've only been really pushing this since about 2012, with our first unit operating in late 2011. If we go and see our references here, you see the biggest units. We've sold units in Turkey, Azores, in Italy, and we can look through these. And then we've just got some photos here to show you some of the units. So this is a 1 megawatt unit on the steel mill. We have here a very small unit. So this is a 100 kilowatt air-cooled unit, which was sold as a packaged box. Here we have basically it's a 4 megawatt geothermal plant in Turkey. Here we have the first geothermal plant we did. It's a 1 megawatt geothermal in Italy. We have a 22.5 megawatt unit geothermal in operation here in Turkey. This is a biomass unit in the south of Italy, air-cooled. You can see the air coolers there above the ORC system. Again, a 1 megawatt in Arezzo in Italy, biomass. Not a unit, but our factory. So this is where we're speaking to you from today. So a quick summary in the last 1 minute of our presentation time. We've told you a little bit about the uses of ORC. We've introduced you to the cycle, explained its advantages over steam, when to use it instead of steam, and I think we'll maybe have to come back to that a little bit with some of these questions in a moment. We've then explained the specifics of the EXERGY technology, which is the advantage we have dictated by our new type of turbine, which, as I said, has been in operation now since late 2011. We have many, many megawatts of that sold now, I think nearly 300 megawatts. And we've just looked at some of the applications. So some of the applications we have done, some of the applications we are looking at. And I think certainly in the heat recovery market, it is very, very attractive to start looking at organic Rankine cycle and a number of different applications. I think now if we specifically turn to some of those questions, and Luca and I look at these together. So the first question we have here is, how does ambient temperature affect the electrical efficiency? And that's a very good question. So the ambient temperature has an effect on the air cooling system. So as the temperature increases, the amount of heat you can dissipate via the air cooling system tends to be reduced. So what you find is that when you have an air cooling system, we design for, let's say, the average temperature of the year. If we look at maybe Northern Europe, I guess an average temperature would be about 8 degrees Celsius. So you can design for that temperature. Then what you would expect is in the winter you're going to have, or at night time, you're going to have a significantly higher power generation. And then in the summer you're going to have a lower power generation. So what we can do is we can actually do a monthly power calculation. So we can tell our customers this is the cumulative power you expect at the end of a year in a certain number of gigawatt hours. But generally speaking, in a very, very basic rule of thumb, if you design for the average ambient and you simply multiply that back by the number of hours of operation a year, you get the approximate power generation that unit will do in a year. Another way of leveling the operation is, of course, water cooling. If you can give a constant heat soak for the unit, you can minimize the ambient effect on the unit over the time. So let's move on to maybe the next question. So we have a question here regarding the steam cycle being used as superheated or supercritical. So the type of cycle we use is generally not a supercritical cycle with our type of turbine. That doesn't mean it's impossible. However, when you do a steam turbine cycle, you always generally go superheated because you need to have superheat in order to recover enough energy in the steam turbine. It's not so essential to go such levels with the organic Rankine cycle. But that doesn't necessarily affect the overall efficiency of the heat recovery system. Is there a minimum size? So moving on from that, is there a minimum size that makes the plant economically viable? What I'd say is it's possible to do these calculations yourself based on the electricity costs you have and based on the situation in your specific environment. So there's no absolute rule of thumb here. However, it is clear that when you get above a certain size, you begin to get the economies of scale. And our plant for the ORC system itself for a 1 megawatt plant will be per megawatt considerably more expensive than our plant cost for a 3 megawatt plant and a 4 megawatt plant and a 5 megawatt plant. So what we are trying to concentrate on is the low-hanging fruit. And I would say organic Rankine cycle systems of above 1 megawatt can give real economies of scale. So looking for the 2 to 3 megawatts would be very good. So I think that's most of the questions answered, and we're very close to our time limit here. So I think I'm going to hand back to Chance. Thank you all very much for your time and your patience this afternoon. And we will be available, and I'm sure Chance can pass on our contact details via this platform. You'll see them there at the end of the presentation. And we are, of course, available to you personally to help with any queries you have. So thanks again for your time, and have a good afternoon. Thank you.
Thank you very much, Anthony. Just to confirm with all of the audience, there were a few questions there that went unanswered, but they will be forwarded on to both of today's presenters and to EXERGY, and you will receive a response in the coming few days. So with that, it just leaves me to thank Anthony and Luca for what was a fantastic presentation, and also a big thank you to EXERGY for sponsoring today's session. To the attendees, today's survey will appear on the screen once this broadcast ends, and we would appreciate it if you filled this out before you leave us today. You will also receive an email tomorrow telling you how you can access the on-demand version of this webinar, or you can access this through our website, which is www.business-review-webinars.com. Please continue to ask your questions, vote in the polls, and interact with all of the widgets as the on-demand version remains interactive. We look forward to sharing further webinars with you, so please do keep an eye out on our website just mentioned, and follow us on Twitter at BRWebinars for daily updates, and join our LinkedIn group, Business Review Webinars. Thank you once again, and I hope you all enjoy the rest of your day.